Okay, in this video, I'm just going to recap what we learned with the disk and the washer method and how to distinguish when we use each of them, and also how to determine if it's going to be a dy or a dx. For the disk method, we use that when we have solid shapes. And for the washer method, we use that when we have hollow shapes. For both of these, we sketch the shaded region, the representative rectangle will always be perpendicular to the axis of revolution. So for both of these, our representative rectangle is perpendicular to the axis of revolution. The disk method creates a circle. So the integral is going to be found using the surface area of a circle, pi times our radius squared, if we're integrating with respect to x, or it would be pi times r of y squared if our radius is with respect to y. For the washer method, our integral is going to be pi times our outer radius squared minus the inner radius squared. How you find the radius here is going to be the top function minus the bottom function for a dx. And the radius is going to be equal to the right-hand function minus the left-hand function for a dy. Over here, our outer radius is the distance from the axis of revolution to the outside edge of our shaded region. Our inner radius is going to be the distance from the axis of revolution to the inside edge. Now I'm talking about the outside and the inside of your shaded region. So for example, if I had a shaded region that looked like this distance would be my outer radius and this distance would be my inner radius. And you still find that distance by doing top minus bottom for a dx and right minus left for a dy. Let me draw a picture for a dy, what that would look like. Something that looked like this, and this was my shaded region. If I was revolving around the y-axis here, I was revolving around the x-axis. If I was revolving around that y-axis, that distance would be my outer radius. This distance would be my inner radius. And you would have to know those functions then that would give you those values. All right, so that kind of recaps everything that we've done so far. All right, so let's look at some example problems here. So here we're asked to find the volume of the solid generated by revolving the region bounded above by y equals 4 square roots of x. That's this blue curve right here. And the lines y equals 4, which is the red curve, and x equals 0 is the y-axis. So our shaded region is actually going to be this region right here. We're going to take this same region for all of these four problems. We're just going to change the lines that we're revolving around. So in part A here, I want to revolve this about the x-axis. When I revolve this about the x-axis, will I have a solid shape or a hollow shape? Hollow. The way you determine that is you look at the axis. If the shaded region is touching everywhere along that axis, it's solid, we would use the disk method. Because this is a hollow shape, we're going to use the washer method. So for the washer method, my inner radius would be the distance from the blue line to the axis of revolution, and my outer radius would be the distance from the red line to my axis of revolution. So my representative rectangle is going to look like this. So to set up the integral here, I'm going to use the volume is equal to pi times the integral from where to where. Well, that means that you need to know what these points are. So this is x equals 0. This point right here happens to be, if you set this equal to 4, you would get x equals 1. So this is going to be the point 1, 4. So my bounds are going to go from 0 to 4. Strike that, not 0 to 4. My bounds are going to go from 0 to 1 because I find my bounds along the x-axis, and this value of x right here is 1. I had to zoom way in on my calculator to get this picture. We use the outer radius, which is going to be what? 4 squared. It's a constant. That outer radius stays the same all the way along from 0 to 1, doesn't it? Minus my inner radius is this function right here. and that's going to be 4 square roots of x squared. So then we would want to clean this up, and that's going to give us pi times the integral from 0 to 1 of 16 minus 16x dx. So we could factor a 16 out, and we would integrate 1 minus x dx. So let's move this up here, and that's going to give us 16 pi times, when we integrate 1, we get x. When we integrate x, we get 1/2 x squared, and we evaluate this from 0 to 1. So that's going to give us 16 pi times 1 minus 1/2 minus 0 minus 0. So that's going to be 16 pi times 1 minus 1/2 is 1/2, and this ends up being 8 pi. For part B now, we're revolving around the y-axis. So when we revolve this around the y-axis, our shaded region hasn't changed. It's still the region bounded between these curves. This point is still the point 1, 4. And our representative rectangle has to be perpendicular to the axis of revolution. So I'm looking at a delta y here. So now my integral is going to be a dy. The variable of integration is going to be y. Is this going to be a solid shape or a hollow shape? This is going to be a solid shape because our shaded region is touching this axis of revolution everywhere. So we're going to use the disk method. What are going to be my bounds of integration? 0 to 4. And for the disk method, we just use pi r squared. My radius is going to be the length of this rectangle as we move, starting down here at 0. It'd be really, really tiny here. It gets a little longer here until I'm all the way out at 4. So how would I represent that function? Well, the function we were told, this blue function, was y equals 4 square roots of x. When I change my variable of integration to y, that length there is going to be the x. So I need to solve this equation for x. So what is x going to be equal to? I'm going to divide by 4 and then square both sides, so that looks like it's going to be y squared over 16. If you just solve this equation for x, you get x equals y squared over 16. The length of this radius is that distance x, and I write it as a variable expression because it changes as that rectangle slides along these bounds from 0 to 4. So this is going to be pi r squared, and this will be a dy. So I'm going to need help with the arithmetic here. So this is going to be the integral from 0 to 4 of, what do you get when you square 16? 256, is that right? That 256 that I got from squaring the 16 is a constant, so I'm going to go ahead and pull it out of my integral, and then I'm just going to integrate y to the 4th power. So that gives us pi over 256 times 1/5 y to the 5th from 0 to 4. And this is why God gave us calculators, so I'm going to go ahead and use my calculator. And that's going to give us 4 to the 5th divided by, open parentheses, 5 times 256. And we're going to change that to a fraction, and it looks like 4 pi over 5. I didn't show the step, and I probably should have shown the step where I do plug in my bounds, because on your test, I actually want to see that step where you plug in your bounds. So that would be 1/5 times 4 to the 5th minus 1/5 times 0 to the 5th. For part C, we're revolving around the line y equals 4. So we're going to be revolving around this line. This is still the point 1, 4. And our shaded region is still this region in between the curves. So when I revolve this region around the line y equals 4, do I have a solid shape or a hollow shape? I have a solid shape, so what method do I use? Disk. My representative rectangle is now going to be this rectangle. Do y'all see that? The thickness of that rectangle is delta x, which means x is going to be our variable of integration. So when we set up our integral, we're going to have pi r squared, where the radius, by the way, the bounds of this are going to go from 0 to 1 along the x-axis because we have y as a function of x, and y as a function of x was 4 square roots of x. So we have y equals 4 square roots of x. So this is going to be the top function, which is 4, minus the bottom function, which is 4 square roots of x squared dx. Remember, the length of this radius is equal to the top function minus the bottom function. The top of that function was 4, y equals 4. The bottom was y equals 4 square roots of x. That's how we came up with our radius. So to make the arithmetic easier, I'm going to go ahead and factor out a common factor of 4 here, and that's going to give us pi times the integral from 0 to 1 of 4 times 1 minus the square root of x squared, close the parentheses first, then square, dx. When I square the 4, that's going to give me 16, so I can pull that 16 out, and I'm looking at 1 minus the square root of x squared. Well, 1 minus the square root of x is just 1 minus the square root of x times 1 minus the square root of x. I can FOIL that out. And when I FOIL that out, that's going to give me 1, okay, that's minus the square root of x, so that'd be minus 2 square roots of x, and then plus x. So when I integrate this, I really don't want to write the square root of x. I'd rather see x to the 1/2 power. Are y'all okay with that? So that's going to give us 16 pi times x minus, add 1 to 1/2, that gives you 3/2 times 2, so that's 2/3 times 2 is 4/3, x to the 3/2 plus 1/2 x squared, evaluated from 0 to 1. So when you plug in your upper bound, that's going to give you 1 minus 4/3 times 1 raised to any power is 1, plus 1/2, minus, plug in the lower bound, and that's going to give you 0, 0, 0. And cleaning up the arithmetic, that's going to give us 16 pi times, common denominator is 6, so that would be 6, 6 minus 8, 6 plus 3, 6. So that's 9, 6 minus 8, 6 is 1, 6. And that's going to be, 2 goes into both of those, 8 pi over 3. Somebody double check my arithmetic, please. All right, so that's 8 pi over 3. All right, for part D now, we're asked to revolve around the line x equals 1. So here's the line x equals 1, and we're going to revolve our shaded region about this line. So here's our shaded region. And when we revolve it around the line x equals 1, our representative rectangle is going to be perpendicular to the axis of revolution. That means that we're looking at a delta y. So I need to write x as a function of y. So x was equal to y squared over 16, we said when we solved earlier for x as a function of y. So is this going to be a solid shape or a hollow shape? So what method do I use? In order to use the washer method, I need 2 different radii. I need an inner radius and an outer radius. My outer radius is going to be the distance from the outside edge of this shaded region all the way here. So my outer radius is going to be equal to the right-hand function, which is 1, minus the left-hand function that binds it is 0, and that's going to be 1. My inner radius is going to be this function right here. It stops right there at the r. So my inner radius is going to be the right-hand function, which is 1, minus the left-hand function, which is y squared over 16. So that's 1 minus y squared over 16. So when we set up our integral, we're going to get pi times the integral from where to where? What are going to be the bounds on my integral? 0 to 4. Remember, this point right here is at the point 1, 4. We look at our y values here to get our bounds on our integral. So it's going to go from 0 to 4 times our outer radius squared minus the inner radius. So that's 1 minus y squared over 16 squared dy. So let's clean this up now. That's just going to be 1 minus, and this I need to FOIL out. So I could write this as 1 minus 1/16 y squared times 1 minus 1/16 y squared dy. So I need to FOIL this out. And when I do that, that's going to give me 1 minus, and I'm just going to FOIL this out here. First terms is going to give me 1 outside terms is minus 1/16 y squared. Inside terms is the same, so that's 2/16 or 1/8 y squared. Last term is going to give me plus 1 over 256 y to the 4th dy. And now I need to distribute this negative across here and combine like terms. Once again, it's the algebra that can trip you up in calculus. So that's going to give us pi times the integral from 0 to 4 of, I've got 1 minus 1, minus times minus is plus 1/8 y squared, and then minus 1 over 256 y to the 4th dy. Well, the 1 and the negative 1 are going to cancel each other out, so I'm left with the integral from 0 to 4 of 1/8 y squared minus 1 over 256 y to the 4th dy. So now let's integrate this. What do I get when I integrate 1/8 y squared? We add 1 to the exponent, that gives us a y cubed. Divide by the new exponent, so 1/8 times 1/3 is 1/24, minus 1 over, what's 256 times 5? 1,280. All right, so we've got our integral done. Now we need to evaluate it using the fundamental theorem of calculus, so that means we're going to plug in our upper bound and then plug in our lower bound and subtract. So that's 1 over 24 times 4 to the 3rd minus 1 over 1280 times 4 to the 5th minus, and then these terms are just going to be 0, so I'm going to just write out the zeros there. And this is why God gave us calculators, guys. 4 to the 3rd is 64 over 24, and then 4 to the 5th is a really big number. What is it? 1024 over 1280? Simplify these fractions, or just go ahead and plug this into your calculator at this point and give me an answer. What's 64 over 24? 8/3? So it's 8 pi over 3. 8/3 minus how many? 4/5? So 8/3 minus 4/5, common denominator is 15. So that's 40 minus, so this is going to be 28 pi over 15. So you see how we take the same region, and just by changing the axis or the line that we're revolving around, it changes the volume of the object. If we have a hollow shape, we use the washer method. If we generate a solid shape, we use the disk method. The challenge is going to be figuring out what is the radius. On this one, we had a solid shape, but we had to use subtraction. I'm sorry, this one we had a hollow shape. This one we had a solid shape, but we had to use subtraction to find the radius because the radius wasn't attached to an x-axis or a y-axis, so we had to use top function minus bottom function here. Does that make sense? Don't try to force a fit when you're solving these problems. Let the picture guide you. Do not try to do these problems without sketching a graph of the two-dimensional shape, labeling the axis of revolution to help you determine what the radius is going to be and what method you use to integrate either the disk or the washer. Both of these come from the formula for the surface area of a circle. Area equals pi r squared. If it's a hollow shape, then you have to do outer radius minus inner radius so that you're getting the shape from the donut there. All right, that wraps up what we're doing today, and we will start 6.2 on Tuesday.